haven't got it.
Great, great. So let's get started. So today we're going to talk about the last, in the section on the streaming algorithms, talk about the last two topics within it. We'll come back to it a bit later in the semester once or twice. These were there was a poll on Canvas. It wasn't perfectly set up, but I gave you true, false answers, and the ones that got the highest percentage of true for interest were the distinct item counting and mergeable summaries for mapping to big data. So we'll talk about these today. Before we get started, let's just kind of remember what is on the schedule. The big thing is the midterm test is tomorrow in class. It's going to be here in class. Wednesday in class. Thank you. So for everyone online, make sure you're in class on Wednesday. The midterm will be taken here. And then we have the clustering homework was due the week before break. It's mostly graded. I'm hoping we'll get this back to you. The plan is to get back to you before the midterm. So I think we're on track to doing that. This is not okay. And let me check something with the videos not working. See if that fixes it. If not, we'll just go. Okay, and then there's a homework coming out, the frequency estimation homework, which will be on streaming more general. It's almost ready to be posted. We're checking a few things, so that'll be posted early this week as well. It'll be due already next week. But the frequency, the streaming stuff will not be on the midterm. Just remember, the midterm will include topics from the start of class up through the clustering section. So you do not need to study for the streaming stuff on the midterm. I'm going to also say that there's kind of been a change we've noticed as instructors in how students have been learning in our courses since around COVID time, and the students have been doing a lot worse on exams across the entire department. And it's mostly not the people who come in class. Okay, so all of you who are here in class, that's great. It's mostly the people who are not coming to class, which is about half of you. And one thing I'll say is I taught this class again for the first time after almost 5 years last year, and the class on average did not do well in the midterm. Okay, I think it was similar difficulty to what I was giving before, pre-COVID basically, but students did a lot worse. One of the issues is I included the streaming stuff in the midterm test before there was a homework that was due on that, so I've removed that. So I had to basically cancel that question last year because people did so poorly on it. So it's only up to the clustering, so that's good. But I want you to kind of not dismiss the test and not just kind of show up without studying on the test. There is a linked practice test. You can see the link right there on the page. The test should give an example of kind of what it's going to be like. What I can tell you about it is that it's going to focus on basically 3 topics, thinking about how you measure distance or similarity between objects, how you do similarity search between objects, and how you do clustering. Okay, those are going to be the three topics. If you look at the schedule, that should not be too surprising. And so like this exam has basically 3 questions. Each one has multiple parts to it. Okay, and so there'll be 3 main things, but then might be some questions that cover breadth across all of the lectures. Okay, so this practice exam was made before I kind of reorganized the topics a bit, and so the kind of the emphasis has maybe changed a little bit, so the questions may not be as representative of the spread of the topics, but I think they are good practice for how hard it should be. Okay, you will not be allowed to use laptops or no calculators on the test. I think this is good. It means the calculations, I have to set up all the calculations, so they should be easy. If you find yourself doing a really hard calculation, you're probably doing it wrong. Okay. You will be allowed to have 1 sheet of paper, front and back, 8.5 by 11. You can put whatever you want on. Okay. I recommend this. The students who do a careful job selecting things and putting it on the sheet tend to do well. It's a good practice to think, what were the main topics? Let me make sure I write down what I think are the important things. I ask you to do this partially because then you don't have access to the full note. You're not searching through. I used to allow access to the full notes, and people would come and they would print out all the notes, and then they'd spend the whole exam searching through the notes looking for answers. Okay, this was not a great way of doing it. This forces you to have something concise and forces you to spend time thinking about what were the main things on there, right? But you can do whatever you want. It can be handwritten. It can be electronic. I don't want you to use a magnifying glass to read. Okay, this has come up in the past. All right, and you can have scratch paper and stuff. It'll be in class. And if you look at this test, if you know the material, you should be able to finish within the class period without a problem. Some people, by their choice, will sit until the very last minute and check over everything. But time probably should not be a problem if you understand the material. Question. They will be like these, but not exactly these.
Like the big 1, 2, 3.
There'll be 3 big questions like this. It'll look very similar. The biggest change is that there'll be the front page will not have a question on it, so it'll start on the second page. But otherwise, it will look just like this. Okay, that way I can come and hand them, and you don't flip them over until time starts. But it will be 3 questions. They'll each have multiple parts to them. Right? Yeah.
We have to write those down in the notes, or is it better to go test?
Yeah, so this is a good example here. So the formula for Jacquard, you should probably know. I may or may not give that to you. The formula for Anberg, which is a more specialized variant of these things that we didn't cover in as much depth, I shouldn't necessarily expect you to memorize this. Okay, so I provide this, and for symmetry, I provide Jacquard as well. Okay, so if it's something really fundamental, you should just know it. If it's something I think there might be confusion on, and I don't want that to be the sticking point, I'll probably copy up the formula so you know it. Okay, so the really fundamental things like Jacquard, you should probably know. There's no guarantee I will put that out there. Yeah.
What about the birthday paradox or the coupon collector problems?
The elements of those could show up on the questions. I have implied they will not be a whole question. Like one of the 3 questions will probably not be on just that. But there may be parts of them that show up in there, but not as the focus of a third of the exam. Yeah. All right. So if I would use this exam to kind of get, if you know the material well, you should be able to finish this in an hour. It probably gives you a good sense of timing. If you think taking this exam, like we didn't spend as long on min hashing in this this semester as we did in the past. But if you think taking this exam is going to take you way more than 80 minutes, then you're like, okay, you should make sure you're studying better. Yeah.
For this, three, the same.
Is what? Is
Like B1 is 3 and then O3, 0, 3. Are they the same or are they gonna be?
yeah, I don't remember. I made this question a long time ago. Yeah, I know. I see that. Yeah, if that came up, I would either clarify it. Hopefully, we don't have confusion like this, or I would allow either way of interpreting it. Yeah, that's a good point. Yeah, I didn't spend as long creating the practice exam and carefully check it as I do the full exams, but hopefully they're not things like this. Yeah.
So if the two find out.
Yeah, I probably did it so they lined up well, but so this probably should be treating it as the same as O3.
Is there a way to access the answer? Is there an answer key for the problems in the textbook?
In the textbook? No, I've not provided those. Yeah. Yeah. If you if you have questions on particular questions that come up, we can provide answers to them probably in the Canvas discussion. And the TA has an extra office hour tomorrow at 3:30 because it's the day before the day before the test, right? So these are good resources to get if you get stuck on something to try and figure out the answer. Yeah, and I try and answer Canvas discussion pretty quickly. All right. Okay. So there's some. Okay, I'll keep talking to block out the sound of the water running someplace. All right. But any other questions on the midterm? Yeah. Yeah. Okay. Great. Well, we'll be here and we'll have the printed out and probably we'll see some faces we haven't seen all semester. So I'm looking forward to meeting the rest of the class. Okay. All right. And apologies, my video isn't working today for those watching online. Okay, so let's talk about the distinct. Okay, let's talk about the two last part of the streaming model. Let's recall the streaming model. Okay, we have as input a stream, which is going to be a data set. We'll write A1, A2, AM. Okay, and this is going to be a set we're going to see in order. So we serve in order and with small space. Okay, and in order on one pass. So we only get to read everything once, and the small space means that the space should be on the order of some, usually a polynomial of log of m, which allows us to count how many things we've seen so far, and it'll also say log n, where n, usually we say each AI is in a set of size n. So think of this could be all of the IP addresses, all the different kind of combinations of words we see in a string of text. It could be all the people we see in a population, all the users on a website. Some extremely large number. So we don't want to see a polynomial and then we see a polynomial in the log of these things. So this would allow us to create a label and this would be a counter, right? So we'd think of this as a counter and this as a label of something we've seen. So it's pretty limited what we can store. And the question is, what can we keep track of in the streaming setting? Okay, and so one thing we like to look at is the frequencies. So we'll say Fj is going to be we're going to look at the set of all the AI in the set A such that AI is equal to the value j. Okay, and the size of this set. This would be the frequency. And so we talked about frequency approximation before break. Today we're going to talk about the what's called F0, which is going to be the number of distinct items j in the that we observe. So it's the number of Fj which is strictly greater than 0. So how many different things did we see? Okay, and so this is really kind of a really important, but kind of twisted to think, how would you keep track of this when you can't keep track of all the different IP addresses or all of the packets running through a router? I want to know how many distinct IP addresses I see. If something is being sent to over and over again, I don't want to count that twice. What we saw before break was that the really heavy things, the really high frequency things, we can approximately keep track of. But there could be low frequency things that occur exactly once, 0 times, or maybe 2 or 3 times. And we want to know how many different things we see without counting the same IP address or the same word or the same customer coming to a website more than once, even if they're occurring multiple times. So when you're looking at websites and valuation of these companies online, a really important measurement they want to know is how many distinct different people come to their site, right? And if you have, these sites try and put some cookie on your on your browser, the cookie will keep track of that you are a unique individual. That's why these cookies keep showing up. And that allows them to give you a specific unique ID in so in the cookie. Okay, they can assign you a unique ID in some way, but they don't want to necessarily keep a counter for all the possible people who come into these places. They want to just keep track of the total number of unique people visiting. Okay, and so this is the distinct items from we're gonna talk about today. And then the second half of the lecture, we'll come back to the mergeability question, which will show us how to kind of scale up to things other than the streaming model, but a lot of the techniques we'll use how they can carry over much more generally to show that the streaming model is not just a toy model, but if you add one more step, which you can usually do, then you can apply it to lots and lots of different settings relevant in mining massive data. All right, so how would you keep track of the number of distinct times in the stream? What is kind of the first key insight we're going to need in order to potentially to make this even possible? What is? Yep.
Keep track of the things that you've seen.
So keep track of the things we've seen so far. Yeah. And we need to keep a unique representative for everything, right? So we somehow need a compact way to maintain information about unique representatives. Okay, so in this case, I've abstracted it, right? We've done this abstraction where there is, the unique representative is this value j, right? And I just say, okay, there's a value j indexed into here, but in practice, it's an IP address, which you may not want to, or it's a word, or it could be a customer representing somehow. We somehow want to get some kind of abstract way of keeping track of unique representative that doesn't depend on what this actually is. So what we're going to use is some sort of, we're going to start with some sort of hash, we're going to start with like some sort of hash function. So that is mapping all the unique things into a smaller domain in some way, or at least into a domain. So everything is unique. We can think of these here, right? So we're going to need to somehow leverage. We're going to leverage a hash function from H is going to go from, let's say, N, or the space of the stream A into some sort of domain, right? We'll say of size K. Okay, and I want to start with the warm-up exercise of how we often maintain which things are inside of like a set using hash functions. So we're going to talk about something called Bloom filters. Okay, who's heard of a Bloom filter before? Is this something you've seen in a data structure class? All right, so this is a really compact way to keep track of what items are inside the set. So it kind of, this Bloom filter will maintain which items S are in A, okay? It's going to have no false negatives, okay? So if something is in the set, I'm always going to be able to say yes. I'm always going to return yes if I'm asked if it's in the set, but I'm going to allow for false positives, okay? And so I don't want too many false positives. I want to somehow minimize the number of false positives, but I want to be able to keep track of this with so using a hash function. And this is a very general tool. And if the size of the set is very small, this is going to work well. I'm going to be able to get not just roughly how many things are in the stream, but also to know I can ask a query for everything and determine whether it's in there or not. All right, and so what I'm going to do is I'm just going to so I'm going to have, in fact, I'm going to have T hash functions. Okay, H1, H2 up to HT. And remember, this process is randomized. The hash functions themselves are deterministic, but I randomly select them from a family. And I can implement this, for instance, by choosing a deterministic one and adding a random salt to it, right? Okay, and then I'm going to maintain, I'm going to also have an array B that goes from 0 up to, say, K minus 1. Okay, so it has K things in this array, and this is going to be an array of bits. Okay, so, and I'm going to initialize them as 0. So I'm initialize all the bits as 0. Okay, but there's only one array of bits. Okay, and so what this does is for AI in the stream, I'm going to, for J equals 1 to T for all the hash functions, I'm going to set the bit at the hash of AI, the jth hash function, equals to 1. Okay, so when I observe it, I'm going to go through all the hash functions. Say I've got 5 hash functions. Sometimes 2 hash functions is enough here. And I'm going to set the bits for all the hash functions to 1 that this item occurs with. Now on the lookup, so on a question, if something is in the array, is Q in the set S? To answer this, I check if H of J of Q equals to 1 for all values J in 1 up to T. Okay, so there's a bunch of shared bits. You know, the hash functions might hash to the same thing multiple times, but in order for this to be, so if I saw something in there, I would set the bits to 1. I never set them back to 0 again. Okay, and it could be that another item hashes to the same spot, but if I have 5 hash functions, then I have to have 5 different things have collisions at the same time. If I have multiple hash functions, the probability of having collision is much lower than if I just have 1 hash function, even if I'm compressing this down. Okay, so I can store, if something is in there, I'm always going to return 1 because I will have set all the proper bits with the deterministic choice of the hash functions to 1. If something is not in there, it would have to have collision in all the hash functions, which would maybe harder to do if I had multiple hash functions. Okay, so this will work well if I am allowed space roughly proportional to the size of the set of distinct items. I can keep track of basically roughly all the distinct items in here. And the optimal thing to do, I want to set K or T. Roughly what I do is you set T roughly equals to the number of hash functions as K divided by the size of S. Okay, so if I have K space, right, then I want to set T equals to roughly, do I get the, yeah, so the optimal thing to do is, but so if I know how much space I have, so this is about the right number of hash functions I should use to get the optimal, to minimize the number of false positives. But if I have more than K items I'm keeping track of, there's by the pigeonhole principle, I'm going to fill up all the bits, right? And in fact, roughly, if I have square root K things I'm keeping track of, by the birthday paradox, I'm going to have a really high probability of having a collision. Okay, even with T of these hash functions. This works well, but not if I'm going to have a very large number of items I'm seeing. Okay, so if the number of distinct items I'm seeing is very large, roughly proportional to the size of the stream I'm seeing, this structure is not going to work. So if I have a very small number of distinct things, this will work, but not if I have a very large number of distinct things. Okay, so I can't, even with hash functions, I can't keep track of all the items very efficiently in this. Okay, so this was a very brief overview of these Bloom filters, but this is not the right answer. And it's partially because it's trying to do too much. It wants me, I want to be able to return any item if it's in the string or not, if it's in the stream or not. I want to determine, is this particular item in the stream or is it not in the stream? Okay, so if I could always check in the Bloom filter, is item in the stream? If it is, I can increment the counter. Okay, but I don't want to kind of I can't keep track of whether the item is in the stream or not, even with this Bloom filter, which is very compact. It's storing stuff as bits. It's only keeping roughly a constant number of bits per item, but it's still, I'm not going to be able to actually do this. Okay. So I need kind of a different way of approaching this problem. Okay. So I still want to use hash functions, but the idea is instead to, let's say, for instance, I have a hash function. Okay, that can go from the space of everything in the string, all the possible objects in the stream, into a continuous value from 0 to 1. Okay, so this is a subset of the real values, right? So I want a continuous value between 0 and 1. We used a trick like this in the stream sampling approach, where we're sampling items from the stream. I gave everything a kind of a random value, and then I selected the things that had the smallest random values. This was one of the tricks we used to do the weighted without replacement without replacement sampling. We picked a continuous hash function, okay, or a hash function with a continuous space of the outputs. And I'm going to start exploring this idea and show that this can partially work, but we're going to get how you implement this will be a little bit tricky. So we're going to not ultimately use continuous values, but let me start by thinking through this. Okay. So what's going to happen is every item we see is going to hash to a different continuous value between 0 and 1. And we just want to keep track of the number of distinct things we've seen. If something hashes to someplace we've already seen before, we don't want to count that again. Okay, so how do we use to keep a count or an estimated count? We're not going to be able to do this exactly. We're not going to be able to exactly keep track of the count of all the unique things. How would we use this to maybe like estimate a count by looking at hashing to a bunch of continuous values between 0 and 1? Let's just say we have a single hash function. What could we use if we are, let's say there's an array or an interval where this is 0 and this is 1. Let's say we're going to up to 1, and we're not going to be able to hit exactly 1. We'll see why when we get to the discrete version of this. And so I'm going to see items. This is going to be the hash value of J1. This will be the hash value of J3. Maybe here is going to be the hash value of J2. This may be hash value of J4. How would we use hash of J5? Maybe this is hash of J6, right? So this would be kind of what it would look like. And each of these is a value between 0 and 1. They're all going to be completely distinct from each other. No actual collisions if the values are the same, unless we're going to have hash of J7 equals J3. Then they're going to map to exactly the same spot, right? So we're going to have the number of things we hash here. Each item, okay, we're going to assume that each HJ is going to be random, in fact, uniform in 0, 1. Okay. And we're going to have a number of the instances is going to be equal to the number of distinct items, right? Which is F0. Wait, let's call it F0, right? So what I know is that we're going to we're going to hash these. Each one is going to be a random location in here. And we're going to get a random location, a random dot between 0 and 1. The number of that we're going to get is going to be the number of distinct items. Okay. And I know I can't keep track of all of them. So I need to keep track of a smaller piece of information. What would be some maybe useful thing I could keep track about these things? Range, maybe? Or I could maybe keep track of the sum of them. The sum is going to converge to 0.5 times the no. Yeah, I don't know if I saw J7. Do I know if I saw it before or not? I don't know if I saw it before. It will hash the same location, but I don't know if I will have seen it before. Because I would have had to have kept track of J3. And even with the Bloom filter, I couldn't keep track if I had seen it before. So I can't keep track of the sum of distinct things. You can keep track of the sum of the total number of things, but not the number of distinct things. Yeah, so someone say the range of things.
Right.
Throw a bin. So I would put down some bins, right? So I could divide this into bins, right, of equal size. And so I keep track of which bins are hit. Okay, so how many bins should I put down? K of them. And then after I've seen roughly K log K by coupon collectors, I will have hit all the bins. So, and I don't know if two things in the same bin are exact copies of each other or if they are a little bit off. So I can't keeping counts of bins. So after K log K things, I will have filled up all the bins. So that's not, it's going to save me basically a log factor. You know, I'll go from keeping track of K to roughly K divided by log K to know when I fill all the bins. That's not a big savings. That's not even a polynomial factor. I need an exponential factor savings here. Okay, so did someone say the range of things, or what's another trick we used? What's something simple I can keep track of that depends only on the number of things I've seen? Number of distinct things I've seen. Okay, so the answer is going to be, I'm going to keep track of the what? The set. I can't keep track of the set of everything. The boundary of them. Okay, well, how if I just kept track of one boundary? This is equivalent to saying gamma. I'm going to say this is the min over AI and A of hash of AI. Okay, I'm just going to keep track of the minimum value I've seen. Just the smallest one, okay? If I see this one again, it doesn't change which one is the smallest, right? So the smallest only depends on the number of distinct items. Each one is uniform randomly, and the number I see is the number of distinct items. So as I get more and more, I should expect to see something that's smaller and smaller in expectation. How close do I get to the 0 point? Now, I might get unlucky and hit something really close to 0 at the beginning, and that kind of fools me. But this should give me some sort of estimate. Okay? And so, in fact, I can keep track of the min of all these things, and I can get an estimate of F0 as 1 over the min minus 1, actually. For some technical reasons, I do minus 1. Okay? But it's basically, I look at 1 over the smallest value. And so this kind of should approximate the total number of distinct things I've seen. In expectation, this is the right value. Not sure. So if I use this, turns out this will give me in expectation, the right number, or it's at least approximately this. It converges to this, but that this will give me the total distinct number of counts, right? So kind of the expected distance from the smallest thing to the boundary, 1 over that is approximately the number of things I've seen. This is what we aren't going to go through the math of exactly why this is the case, but you should think as if I get something smaller and smaller and smaller, I expect to have more and more of items in the distinct items in the set. You can see it only depends on this hash function being random, and that only depends on the number of distinct items, not on the total number of items. Like the average or the count, that would depend on the total number, but the number of distinct things, and I can keep track of this easily. Just the minimum value. I only have to keep track of one value now. Okay, this isn't a great estimate because, well, I might accidentally get a really small value at the start. Okay, so it's not a great estimate, but I can amplify a very crude estimate. Okay, so instead of one hash function, I select T hash functions. Okay, with hash 1, hash 2, up to hash T. They're all IID from some hash family, right? So, and then I can create that gamma plus is going to be, or let's say gamma bar is going to be 1 over T, the J, gamma J, where gamma J was from the hash function HJ, right? Maybe we'll call it. Okay, so I can create an average value instead of just keeping track of one value. Each one will be between 0 and 1, and it will give me approximately the right answer. And so then I can create F bar 0 is going to be equal to 1 over gamma bar minus 1. And if I set T equals to 1 over epsilon squared, 1 over delta, then with probability 1 minus delta, I can have that F bar 0 minus F0 is less than epsilon times F0. So I get relative error here from the true value. So up to, if I set it to, I keep track of 100 times 10, so roughly 1,000 of these hash functions, I can keep track of this independent of what this actual size is within within roughly 10% error, right? So if epsilon equals 1 over 10, and let's say delta equals 1 over 10, so I'm 90%, I'm correct, then I'm within, then F bar is plus or minus kind of 10% of the true value. Or F, let me write this a different way, equals the true value plus or minus 10% of the true value. So I get within 10% of the true count using roughly 1,000 counters. Okay, 1,000 of these min estimates. So I can do something like this. All right, so this is approximately the right idea here, but there are a couple of issues with this, and why there's some algorithms that kind of are more famous and work even better than this. I'll show you one more kind of cool trick of how to do better. And so I can actually, there are two issues with here. One is that the issue number one, the failure probability is high. So I have 10%. This setting delta equals to 1/10 means that 10% of the time my estimate is worse than this, which is bad. If I want it to be 1% of the time, I need to increase the total number of counters by a factor of 10. Okay, which is, I can make a trade-off which is better. Issue number two is that I have to maintain a continuous and very small value. Okay, so gamma, right? So I'm keeping track of these gammas, which are the smallest thing I've seen so far. And that means I need very high precision on the very small kind of parts of this. And so I could use a double or a float, but how real values are stored in a computer is kind of mysterious, and it's hard to account how much accuracy we have. And so it turns out I can do better than maintaining these continuous values. I can do something with bits, which is much more clever. So I'll show you something that will solve this continuous value instead. Okay, let me quickly show you how to amplify the probability of failure. Okay, and this is through what's called the median trick. And so this is a very common trick that shows up in a lot of places. And so I'll just do this quickly. So I'm going to run before the algorithm from before with epsilon equals epsilon, but delta equals 1/2. So the probability of failure is 1/2. So now the total size is going to be 1 over epsilon squared with no dependence of delta, the probability of failure. I only have 1/2 probability of failure, but now I'm going to do this with uppercase T, which is going to be log 1 over delta copies. Well, let's say 2 log over delta copies of this. Okay, and so each one is going to have the property that F0, and I'm going to run T, uppercase T of these instances, and with probability 1/2, they're going to be within epsilon times F0. Okay, so that half of them are going to be close enough. The probability of failure was 1/2. So I want to get a single estimate from these T instances, right? These are the T instances here. Okay, and half of them are going to be within the right value. So I'm actually going to get no more than half are going to be bigger in this way, and no more than half are going to be bigger in this way. And I have 2 log delta to play with. Okay, so the probability of failure, so what I'm going to do is I'm going to take the median of these. So this one will be the median of T instances. Okay, so this median of T instance is outside of this acceptable epsilon range only if more than half of log 1 over delta of them that are on the smaller half have more than epsilon over F0 error, too much error. And they're each independent, so the probability of each of them drops the probability by half. Okay, so that means that after log 1 over delta of them, the probability of more than half of them dropping to having more than epsilon error is going to be at most delta. So I've gone from a dependence on 1/delta to a dependence on log 1/delta by doing this instead, by creating these constant probability failure things and taking the median of them. Okay, so this is called the median trick, and this shows up a lot in these algorithms. So I just have to get constant probability failure, and then I can amplify that to only logarithmic copies. Now I can drive the probability failure much lower here. Okay, I want to get to what is cooler and more famous is this algorithm which is heavily implemented and used within these kind of large scale systems. All sorts of tech companies have implemented this HyperLogLog algorithm, and variants of it. There's been a lot of follow-up work that twiddled the last 5% of it, but this is the main idea, and this goes from continuous representation of gamma to bits. I'm going to represent with bits, and there are going to be two kind of, first I'm just going to say what happens if I represent it discretely with bits, and then there's an extra trick where I can get an extra log factor improvement, and that's why there's HyperLogLog. There's something called HyperLogLog that got another log factor improvement, but it was really in the weeds. We're not going to go through that. Okay, so what happens when I represent? So I'm going to hash now. AJ is going to map to some string of bits, 0, 1, 0, 1, 1, 0, 1, right? And I'm going to do hash of A2, and I'm going to do a string of bits, 0, 0, 0, 1, 0, 0, 1. Okay? I'm going to have these represent a number between 0 and 1. Okay? This will represent a number between 0 and 1. It can't do all numbers, but what's going to happen is this first bit is going to be worth 1/2, this one 1/4, this one 1/8, this one 1/16, this one 1/32, 1/64, 1/128. Right? So each bit will be worth this much. If I have all ones, I can't quite get up to 1. I can get up to just less than 1. If they're all zeros, I get exactly 0. Okay? So for instance, this one is equal to 1/16 plus 1/128. Okay, this one is 1/4 plus 1/16 plus 1/32 plus 1/28. Okay, so I can represent the values this way. Okay. One question you should have: how many bits do I need? Right. So I need roughly log base 2 of F0 bits. Right? That's roughly the number of bits I need, because I expect if I have F0 distinct items, I expect to only get all zeros roughly once if I see F0 distinct things. Right? Each one is random sequence of bits. So the probability, so the probability of getting all zeros is roughly is 1 out of 2 to the F0. So I need log 2 of those bits to represent everything, probably a few more to make sure I don't, you can say twice that many bits should be probably safe, even less than that. Okay, but roughly log base 2 of F0 bits. Okay, so now if I want to keep track of the smallest one, let's say I've got a new thing which is coming in, H of A3 maps to 0, 1, 1, 0, 1, 1, 1, 1. Okay, this one was currently the smallest thing I'd seen so far, right? This one is smaller than this one because it's 1/16 plus something. This was 1/4 plus something, right? So this one is clearly smaller. As I'm getting these bits coming in, when can I determine that this one is potentially smaller than the one I've kept, or I can discard it because it's not the smallest? As soon as I see a 1, I can determine that, basically. If this 1 occurs before the smallest one here, this is the 4th bit was a 1. As soon as I see a 1 in the 2nd bit, I'm saying, well, this one is not the smallest. I can ignore it. All right, and this happens again, right? H of A4, 1, 0. Well, actually, as soon as I saw the first 1 here, this is enough information, right? This is enough information to know it's larger than this one. So the idea is, what if instead I just kept track of the location of the first 1 bit? Is this enough? How good of an approximation of the smallest value? Remember, I can turn the smallest value I kept track of into an estimate. How good of an estimation of the smallest value is this? Is it off by, say, a factor 2, a factor 10? If everything after it's all zeros, I get the exact value. If everything after is all ones, well, 1/32 plus 1/64 plus 1/28 is still smaller than 1/16. Right? So it's no more than double if I ignore this stuff. So if I just keep track of the smallest, the first 1 bit, that's a factor 2 approximation. Okay? So just the first 1 bit gives me a 2 approximation. Okay? And if I get a 2 approximation, I could use the previous tricks I talked about to keep track of multiple hash functions and the median trick to amplify this to get a good estimate. So just keeping track of the smallest 1 bit is enough information here for 1 hash function. It's kind of a rough thing, but it's enough. Okay? So then so then how would I store this? So I just store it as 0001. I still need to store all the bits, right? So storing the first 1 bit. So how much space do I need for that? Still log bits. Do I still need log of F0 bits because it might be at the end? No, I don't need to store all the binary information. I just need to store its position. So this requires log of F0 bits, because I can represent this position in this position in binary. So if this is the 4th position, that only takes 2 bits. If it's the 17th or the 15th position, right, that's log base 2 of 15 only requires 4 bits, not 15 bits. So I can actually store, if F0 is a billion, I roughly only need to store log of that number of bits. So I can really, really compress this. And so using this is called the HyperLogLog sketch. I keep track of a number, maybe 100 things that each keeps track of the position of the largest bit I've seen, of the first 1 bit I've seen using this hash function. But I only store that position in binary, right? So and that means I get a log F0 of the bits I need to store to keep track of that. So it's a really compressed representation. Okay, and so this allows you to do really compressed, and there are lots of tricks under the hood of how fast you can update it and how much you can optimize it. But this is the main idea. Okay, so this is famous work from Lajolet and Martin. Okay, so it's a very kind of cool idea when you see this, hopefully. All right, so this is how you would keep track of distinct items. You can hash them with the hash function, only keep track of the smallest random value you've seen. That gives you an estimator of the total number of things you can see, and then you can amplify it by keeping track of multiple and averaging them and taking the median. And this bit compression allows you to really store each estimator in a very small number of bits. Okay, so it's something you can store like a billion things at like within 1% error and roughly 1 or 2 kilobytes of space. So it's a very, very compressed representation. Okay, any questions on this distinct item counting before we kind of move on to the last 20 minutes? This is kind of neat or too much kind of in the details? Neat thing to know. All right. Okay, cool. This is one of the, again, like the sampling and the frequent item counting, this is one of the next most kind of famous things in this space. Okay, for the rest of it, let me talk about the mergeable so summaries. And this will allow us, this is kind of a simple idea that if you can handle and approach this simple idea, you can extend all these streaming summaries to lots of large data kind of settings. And so we're going to think about a summary as an approximate data structure. So we're going to think about it like a class of data structures. And so far, these data structures can allow for 2 types of operations. We could insert one item, right? You're reading the stream, you see a new item, you have to quickly insert it somehow in your representation. And it can return an approximate, sometimes it's exact, like the mean, query. So maybe just like the mean, there's only one thing it can return, the mean. Other times it allows like a query, like the frequent items query. What is the approximate frequency of this item? Okay, so I can insert one item and I can return a query. I can't do a deletion. Deletions, sometimes I know how to do for the count sketch, the count min sketch. I could also do deletions under some limited type of deletions. A lot of the other ones, I don't know how to do deletions. Okay, what we're going to talk about is a new operation called a merge operation. Okay, and this is going to take in this summary. So it's going to take a merge of summary A and summary B, and it's going to output a summary of A union B. Okay, so A is going to be one stream or one thing. I've inserted one item at a time, perhaps, or done other merge operations. And B is going to be a one disjoint stream. Right? So it could be items I'm sampling from or approximating the frequency or a bunch of other things we haven't talked about. And I want a summary, and the summary has the big thing we focused on was the space, which is going to be parameterized by an error. So space will be some function of the error, maybe times that it's like some number of counters and labels we're keeping track of, right? So e.g., either these summaries were 1 over epsilon, this was like Mish agrees, the count sketch, or S1 over epsilon, we 1 over epsilon squared. This would be like the size of the sample we would often need, or the F0 sketch. We basically need 1 over epsilon squared things. Okay, and so there's some trade-off here. And the key is we want SAUB to have the same size guarantee trade-off. Okay, so I needed to have the same trade-off as I did for the original sketch on the merge. So I need to be able to take 2 summaries and have the same sort of space guarantees. I don't want to need to double the amount of space. Then if I do a bunch of merge operations, the space is going to blow up. So I want to be able to do a merge operation without blowing up the space of the summary. You can sometimes, some cases, figure out how to limit the blow up through other things. But in this case, we're going to say the same guarantee. There's no increase in space when I do a merge operation. Okay, so the key is no increase in space or air. Okay, so I'm going to have the same air guarantees and the same space guarantees. This is going to be the key thing I'm going to have here. If I can do this, it's going to allow me to do kind of adapt these summaries to lots of approaches. We'll talk about how to make summaries can be mergeable. You can do the merge operation in a second, but let me talk about things you can do with things you can do with merging. So with merging, okay, so this is again a bit of a data structures lecture, but this is what was requested in the poll. So with merging, for instance, I can have stream A and I can have stream B, and I have a small summary, SA and SB, and then later I can do a merge operation and get the summary A union B. Why would I want to do something like this? It could be that, I mean, it's not just two things, but I have two routers at different parts of the internet, and I want to have a union of their information. Or I'm dealing with so much kind of traffic coming into my website, I can't have a single machine that's keeping track of all the statistics. I need to route some of the traffic to a bunch of these kind of different machines handling all the traffic that's coming in, right? If you're making a query on Google or on ChatGPT, there's not one machine, really powerful machine that's handling all these things. They're sending it out to a whole bunch of different machines. In fact, a lot of the queries are cached different places, so they never even make it back to one of the data centers. But so you have different machines handling all the different queries. And so if I want to create a summary of the union of all the data, I can't keep a summary in a streaming setting on any one of these. I have to somehow parallelize this. So I can do this in parallel, and then I can merge them together later, or there's some models where you can periodically send some updates of the summary to a central site that aggregates everything to keep track of the total summary of everything, right? So by allowing this merge to happen, I don't have to worry about if my error is accumulating as I'm putting these summaries together. I can just, do everything in parallel and combine it together later. So as long as I know my error is not going to accumulate at the end. Okay, so this is one thing I can do. Another example is that my data A, this is my data set A, is coming in a sequence, right? This is A1, A2, here's AI, and then I'm at this point AT, and I say, I want to know about what happened, not since the start of time, but only up to this time here. I want to somehow make a query that only depended on the most recent things in the stream, because these happened last week. I only want to know what happened in this day, approximately. Okay, so now if I kept a whole summary of everything, I wouldn't know how to extract the information from this recent query. Okay, so what I can do instead is I can group stuff together into these blocks. And in fact, I can make these blocks more fine the more recent they are. And in fact, I can group this, usually the old stuff I can group together as as one old a big summary. And I have this block here and maybe this block. And so then based on where the query is, I grab the relevant blocks and then I do a merge operation on the fly. And I get a summary here that is specific to the query. I might be off on the boundary a little bit. And so this works for types of summaries where if you're off on the boundary by not too much, you're still going to get an accurate thing. So it has to do with the count. The count cannot be off too much if I get the boundary a little bit off. There's some details on which ways you can use this, but for a large class of summaries, if I can do a merge quickly, then I can store snapshots and merge them in the stream and merge them together later. And I only need like a logarithmic number of these snapshots. I have to keep track of total. Okay, and so this allows me to have queries that only depend on the recent parts of the stream. Okay, so these are examples of things you can do if you have this mergeable operation on the summaries. And so then it's not just the streaming paradigm, but it allows for lots of different kind of queries in this big data setting where I can process streams in parallel, or I can run something on MapReduce or kind of Spark. And then I can create summaries in parallel and merge them together afterwards and not worry about the error blowing up in the process. Okay, so let me quickly tell you about how to make some of the summaries we talked about mergeable. Okay, let's talk about sampling. Okay, sampling. How do I create a mergeable sketch for maintaining a random sample? You remember how we created the mergeable sketch before? The summary before for the sample. We talked about two approaches. One was the reservoir sampling, where I would, every time I saw a new item, I would, with some diminishing probability, kick something out of the reservoir and replace this one thing. The other one was for each AI, I generate a uniform 0, 1 random value, and I maintain the minimum UI. So I maintain the AI, which has the minimum value of the UI, right? We talked about this with respect to the weighted sampling approach. This allowed it, you could do something like this with weights, but this works for creating a one random sample. And if I want K things, I can create a UI for each of the items and keep the K smallest values. Okay, so how would I merge two summaries like this together? All right, so A gave me a summary of U1, A1, U2, A2, U3, A3, right? And so it's not the first three things, but it's the three things I've kept in the summary. And B gave me U1 prime, B1, U2 prime, B2, and U3 prime, B3. How would I merge this into a single summary where I'm keeping track of K things here that works for A union B? So U1, U2, and U3 were the smallest three uniform random values I saw when processing the stream A. And same with U1 prime, U2 prime, U3 prime for the stream B. How would I combine these together? Yep, I just take the three smallest. So I take the three smallest of these, and so I take the three smallest or in general, the k smallest. So U1 prime, B1, U1, A1, and U2 prime, B2. This is my new summary. Right, I just do a merge sort on these, and I stop once I have the k smallest ones. I need to compare the first two, and then I select this one, then I compare these two, select this one, and so forth. Right, and the k smallest, if I had seen them in any other order, but the way I generate the uniform values was somehow kind of did not depend on the order I saw them, then these three would still be the three smallest, even if I saw A and B in any order in the string. So it's still going to be a random sample from the string. Right, and if I wanted, this gives me a without replacement, because I have k things that I've chosen, kind of, and they're not copies of each other. But if there was with replacement, I can just run k of these in parallel and only keep one thing in each of the samples. Okay, so this is how I do this. This makes this form of a sampling summary to be mergeable if I keep track of the top k. And anything that's keeping track of the top k instances of something, I can just do a merge sort on the list of the top things based on what I'm sorting them on. Okay, the next one will be simpler, the count min sketch. Right, this was approximating the frequencies, and this, if you remember, this had an array of 1 up to t hash functions, h1, h2, ht, and 1 up to k of these, and this had this array, and each cell had a counter, right? And when something came in, I used the hash function to index into this row and update the counter for something I saw. And then I return the minimum over all the hash functions, all the rows, to get an estimate. Okay, so I have two streams that are both going to make a count sketch that looks like this. It's an array of counters. They share the hash functions. The hash functions are known ahead of time. How do I combine two sketches? These count sketches like this. Do what? Not the mean, even simpler than the mean of the two count sketches. I'm just keeping track of counters, right? Trick is this is a, what if I just had one counter? I'm just keeping track of how many things are in the stream. I have a counter for stream A, a counter for stream B. How do I know the total count of A and B? Not distinct counters, just individual counters. How do I do that? The sum, I just add them up. So now I have an array of counters that magically give me an approximation of all the frequencies, but ignore that. I just want to keep track of how the counters combine. What do? I just take the sum, right? I have this for A, and I have another one for B, and I just add them together, right? I just add together all the counters. Just add all counters. Okay, and there's a whole class of things called linear sketches that basically map things randomly into counters and just keep a bunch of counters. Some of the counters are negative even in some instances. And I can just always merge them by adding the counters together, as simple as that. So if I just have counters, I just have to add all the counters together, makes them mergeable. All the guarantees go through just like that. You can, little exercise to think about. Okay, how about the F0 sketch that we talked about today by Logile. This was the HyperLogLog sketch. What was the core thing? We kept 1 over, we're going to basically keep t times t, which is 1 over epsilon squared times log 1 over delta of what? What were we keeping track of? This many copies of? It's basically a counter of where the first 1 bit is, right? It's the max first 1 bit. Right? So I'm going to that many copies of finding the max first 1 bit, and then I need to combine them together by averaging them and then taking the median of some averages. Okay, but I keep track of the max first 1 bit. I just on merge, I want to take the max. I'm going to have 2 different things keeping track of for a particular hash function. What is the first 1 bit? And I'm keeping track of the maximum instance. So I just take the max of the two instances. Okay, so again, this is mergeable. Okay, there are optimized variants of this that maybe are 1 or 2% better sometimes that are not mergeable, but the standard one is mergeable. Okay, I will stop here. But I'll ask you to think about the Misha Grease sketch is the only one I didn't talk about yet. This one is also mergeable, but it requires a little bit more cleverness, not too much more, but you can think about how that might be mergeable, and I'll let you kind of think about that on your own. But I'll stop here. Don't forget that the midterm is Wednesday in class. Bring your cheat sheet. You get 2 sides of 1 paper and look at the practice test. The TA has office hours today, then again on Tuesday, and ask any questions about stuff on Canvas. Access to what?
Can you post the result, the answer?
The answers. Let me see if I have them someplace, and if I have them, I'll maybe post them on Canvas. Okay. But if you have, in the meantime, if you have any particular questions on them, you can ask, and we'll answer on Canvas.
So the calendar says we're going up to clustering, which is 10.3. And then when I go to the book, the exercises in chapter 10, I mean, this is the Markov chain problem.